You have the choice of looking stupid or being stupid. If you don't ask the questions, you're going to be stupid. A degree in mathematics is a license to explore the universe. People tell me they didn't like math. And I answer, they never saw math. Your best math students in high school probably think that math is about answering questions. But you read about Einstein, and that's not what it's about. It's about asking questions. In 1905, Einstein asked a question. How is it possible to have a speed of light which is independent of who measures it? That's not some famous problem that he solved. It's he created his own problem. People spend 12 years solving problems. How often are you just asked to create a new problem? If you are in competition with 100 people, and it can be a cooperative competition as well, we can help each other out. But if 98% of them are spending all their time on solving known problems, and only 2 of them are thinking about creating new problems, where is the opportunity for you? It's on creating the problems. That's the open field.
You coined the term chaos in mathematics. What is chaos?
Clap your hands in front of your face. That's your way of communicating that you think the pendulum has stopped flipping. But the blue pendulum goes through 360 degrees. It flips through.
Can we play?
Yes. And the game is afoot. Make a tiny change, 1 degree change. What happens if you look at the different solutions? If they behave differently, quite a bit differently, then we would say it's chaotic. So a change in initial conditions of a small amount makes a big difference. The most important thing to do in life now is to master the AI. Your real goal in dealing with the AI is to control the AI to do what you want. That's not always easy. So this should be your goal for the next 5 years, the next year, the next month, the next day. Is coming down the pike, down the highway towards us. We have to be asking it questions to stay relevant. It's a 3-segment piece.
Amazing. I have MC Escher in my room. I like MC Escher.
This is a force-damped pendulum. It's a mathematical thing. All 3 pictures are identical except for the color scheme.
I see. Interesting. All right. I shall make an introduction. So, hey guys. Welcome to another episode of Wandering Thoughts. Today I'm joined by Professor James Yorke. Professor James, you are a professor of mathematics and you are a pioneer in dynamical systems and chaos theory. You introduced the term chaos in mathematics. I wanna hear a little bit about yourself and your area of expertise to begin with, if that's okay.
Well, sure. Glad to be here. Thank you for inviting me. Well, I got interested in science when I was in the 4th grade. I was I was on a tour of a planetarium in New York, the Hayden Planetarium it was called, and I just fell in love with these astronomy, with the astronomy, with the planets. You see, if you're in the 4th grade, you really can't understand much about stellar structures, no matter how hard you study. But planets, we can understand. I mean, Jupiter is 88,000 miles in diameter. That's the units we used back then. And that's if you go through it, but it's fat. It's 80,000 miles through the pole, but 88,000 through the equator. And it's 5 times as far from the sun as the Earth is, and all kinds of these statistics, which I just went to the library every day after school and reading about this stuff, and that's how I got interested in science.
Did your teachers aid you, and did they facilitate you in helping you grow your interest in science?
Interesting question. I don't think so. I just had an interest in science, and I just kept following up on it. Somebody from Japan asks me, do Americans like math puzzles? See, I liked math puzzles, so I'm answering your question. And what I said is, back when I was in high school, there was a famous series of articles in Scientific American, and which really got people interested in math. Nowadays, it's gone. There are no math puzzles anywhere you look. So my answer to him is, they never see math puzzles. They don't know if they like them.
Interesting.
And another aspect of math, people tell me sometimes they don't like math. They didn't like math. And I answer, they never saw math. They go through 12 years of school. Even if they take math every year, they don't actually see what I think of as mathematics. One reason is students so dislike word problems that they aren't shown word problems. But word problems relate mathematics to the world. And if they simply say, what is the square root of 2? Can you calculate it? So you've got some procedure. This isn't mathematics. It's a procedure that's like typing. There's just some algorithm you've got to follow. Whereas thinking about how you model something, but what are the mathematics of it, that's quite a bit different. For example, one topic that comes up is balance of payments of countries, right? And, China ships more to the United States than the United States ships to China. Oh, this is terrible. But what's happening is it's not a question of one buyer. You look at the whole problem and you say, well, look, how much is America buying from other countries totally, and how much are they buying from us? And that becomes a different problem. And if the United States is constantly borrowing money and spending it, then obviously money is going to flow out of the United States. They're going to buy more than we're taking in. Or if people in foreign countries want to invest in America, that's money coming in. But looking at one country, it's not the problem. So I'm simply saying this is a way of thinking about the problem. What is the whole problem? Not what was one little piece of the problem. And word problems are hard. You see, teachers are good at teaching procedures. Like, how do you calculate 77 squared? And you know how you go through this but they aren't very good at teaching how do you look at a particular problem that's a word problem. How do you convert it into mathematics? It's tough for everybody. So I say they haven't actually seen mathematics. And my goal is not to come up with better algorithms for doing things, but it's to come up with ideas that surprise people. Back to you.
It's interesting. So it's almost, if I understand correctly, the level of abstraction almost becomes higher, and problems lose their, I guess, their ability to become relatable to people when we just think of it as procedures such as what's the square
Yes,
root of
yes,
2, and that
right.
makes people also lose interest, kind of.
Well, they may or may not be good at algorithms. Like, for example,
Okay.
if you want me to square 777 right now in a paper and pencil, very likely I'm going to make a mistake. Okay. Does that mean I'm no good at mathematics? Yes, according to the algorithmists. But in fact, I'm pretty good at mathematics in a more general sense of working with mathematics. And so if the algorithms are independent of application, then, but it's not going to be a fixed application. Do you always use the same application? Unless you're in accounting, perhaps that might be something. Certainly accountants have to apply mathematics. But basically, they never see math as an abstract, as an application to problems. Things you have to think about.
So what what is mathematics for you?
Somewhere on my webpage, I have a statement. A degree in mathematics is a license to explore the universe. Okay? The universe, that includes world economics. It includes biochemistry. It includes all kinds of things. But that the facility to translate between biochemistry and mathematical algorithms, that's what enables you to use mathematics. Does that answer?
Yes, and so how the chaos theory is quite well. Like the first thing that comes to mind is Steven Strogat's book on applications of nonlinear dynamics on different fields, and yeah, I think pioneers like you are quite well have applied chaos theory and nonlinear systems in quite a variety of fields. I mean, I was going through your papers this morning, and I found one, if I'm not mistaken, even on like sexually transmitted diseases, I think.
Yes, we came up with an idea on AIDS. We published a paper in this, uh, and what we basically said, this was in something like 2003, and we analyzed a previous paper which says that AIDS is a person with AIDS is most dangerous in the first couple weeks, and they didn't tell how that they said these facts in the abstract, and they didn't tell how they got the ideas in the paper. So we tried to duplicate them, and following basically their outline of ideas, but doing it more systematically. And we came up with the opposite result, that that what happens with people with AIDS is they're infectious initially, and then the infectious untreated, the infection goes kind of into a background. They become much less infectious. And then after maybe 8 years, they get very infectious. So it's stage 1, stage 2, and stage 3. And we found that and stage 4 would be actual full-blown AIDS, where they're really sick. And we found that stage 3, they're going to infect more people. Now, this is very important, because if you were the health department, there's no way you're going to detect somebody who happens to get HIV in the first month of their infection, and therefore you can't do anything. But you could infect people who come down with gonorrhea or syphilis or some such thing, and also check them for AIDS, and therefore you have a chance of intercepting them before they get really infectious. And so this is the idea we put forward, and a few years later, virtually the same problem was declared by science as the breakthrough of the year. Every year they have one item in December that's the breakthrough of the year, and it was this idea that you can intercept people after several years. Now, they didn't refer to our paper, but basically that's what we came up with. And our paper, unfortunately, didn't have much of an impact. I mean, of course, one of the ideas is to have impact, and so sometimes you don't succeed, especially when you're working in a variety of different fields and you're a newcomer into this field and people don't listen to you. So
Um. So okay, someone gets their degree in mathematics and has now a license to explore the universe. How do you start using the theoretical knowledge you've gained and you start to apply it into these real world problems? Or how do you, yeah, how do you start applying the knowledge? How do you identify problems? How do you start to systematize? an issue? How do you find the variables?
Sure, there are a lot of different answers, but here's one. In the late 1990s, reading the newspaper, that's a window into the world. And reading the newspaper, we found about a group that had determined the DNA sequence of a bacteria. First time it was ever done. And this was at a time when people were working on the Human Genome Project, trying to find the DNA of the human. But this was ahead of that because a bacteria has much, much, much less DNA than a human. And so the DNA is a sequence of letters, A, C, G's, and T's, and we want to determine the sequence of the A, C, G's, and T's for the bacteria. And lo and behold, this group had successfully, with when uncertainties, they determined a big fraction of this particular bacteria's DNA. And I had a student who was an extremely smart student in computer science and said, well, why don't we think about the problem? They break the DNA into little pieces of maybe 500 letters. And then these are overlapping and you want to put them together. It's like a jigsaw puzzle. It's very much like a jigsaw puzzle, but just on one line. And see how much of it you can determine. And so we did this. And after a couple of years' work, we wound up with creating our own, we called it a genome assembly program. And it was very effective at both very big genomes and at tiny genomes. And at one point, we had analyzed some pine trees, and pine trees were 10 times bigger than the human genome in terms of the amount of DNA. And we were able to determine that. And also when our program was applied to tiny things like bacteria, tiny DNA chunks, it was about the best. So it was a tremendous program. So you read a newspaper article and say, hey, this is the beginning of something new. It's like right now, what's new right now? What would you say is what's new right now?
The first thing that comes to mind is artificial intelligence.
Exactly. And much more so when I was talking about this DNA being new, this was a little niche thing at the time, but we saw it as something that was going to had a lot of potential. But nothing compares with AI today. Everybody has to be dealing with AI. On my phone, I have 5 apps that are AIs.
Me too.
And so you can see, let's see, does it focus? It focuses.
Yes.
Chad is on top.
I can see Grok too.
Grok.
Gemini. Yeah, the same as I have Claude too.
Right.
Yeah,
So
ChatGPT.
this middle line here, yeah, right? Oops, you got this.
That's okay.
So in any case, you have a question, ask it. Keep on asking it. And people, this thing is coming down the pike at high speed. It's getting more important and more important. I was giving talks at the University of Maryland on AI in 2017, year 2017, and so on. But this as a bystander, not as an expert. But so I called it my book report because I wanted people. A person shouldn't have to speak about only things that he's a real expert on, because when he's a real expert on, he's going to very likely drill down to material that people are less interested in. And as a bystander, I've always been interested in chess. And one of the big AI breakthroughs early on, I think it was 2016, was the AI program by DeepMind, where they wound up with a wonderful chess playing program. And I gave earlier this week, I gave a Zoom lecture in India for 2 hours. on AI and how AIs think. And particularly, I was emphasizing how the chess playing program thinks, because it's much more into reasoning than ChatGPT is. ChatGPT is like a very smart encyclopedia, whereas the chess playing machine actually, there's no encyclopedia about it. It's simply figuring out what it's going to do. So it's much more akin to our reasoning. And there's a book by Kahneman, Daniel Kahneman, who got a Nobel Prize in economics, Thinking, Fast and Slow. And the book's about many aspects of thinking, but I like the title, Thinking, Fast and Slow. What he's basically saying is that there are two kinds of thinking. There's fast, intuitive thinking, and then there's slow, rational thinking. And what you're doing is you're using, he calls it system 2, is the slow thinking. You're using system 2 to look at the ideas that system 1 came up with. And it's to say, most of the time we're using system 1 just automatically. You're walking along, you're not figuring out where your feet are going. It's subconscious. So another word for system 1 is subconscious. And here's a question. Have you often given a tip in a restaurant?
Of course.
Okay. Who'd you give the tip to?
The waiter.
And who's responsible for making the food?
The chef.
And how often have you tipped the chef?
That's a good point. Hopefully that money goes to a jar for everyone.
Well, it depends on the store, right?
Mm-hmm.
But
That's a good
very
point.
likely the chef gets paid more because they don't get much in tips.
Mm.
Here's the thing. That chef is below your consciousness. You don't see the chef. You don't see the chef cooking. And yet the chef is the most important part. And what I'd like to suggest to you is that subconscious thinking is the most important part. Okay? Now, there's a theory that says something like, if you become a real expert in something, playing the violin, piano, mathematics, you have to spend 10,000 hours. You will have spent 10,000 hours getting there. It doesn't mean you can get there by spending 10,000 hours. You've got to, but if you get there, it has taken you 10,000 hours. Okay. What you're doing is you're, in some sense, training your subconscious. So, for example, you think of these very complicated patterns of a pianist. They're not thinking through every keystroke at that time. That's because they have thought them through in the past. They become subconscious reactions. Okay? Now, the idea of subconscious is at least 200 years old. I think David Hume talked about subconscious thinking and conscious thinking. So I'm not trying to say something new. I'm just trying to say that if you take these two and you try to weigh them in comparison with each other, that the subconscious comes out to be tremendously important. Whereas if we're trying to train ourselves, we think we're training the conscious part. But the conscious part looks at the subconscious. Now, what I found is that there's a way of evaluating this. Usain Bolt had the world record in the 100 meters. And now if we take 50 times longer race, that would be 5 kilometers. And so what are the chances that he would win a 5-kilometer race in a high level competition?
But much less.
Almost certainly you wouldn't see any sprinter in a 5 5-kilometer race. It's just too different. Now, there's no way to measure that I know of to who is the fastest mathematician in terms of thinking, or the fastest physicist, or the fastest writer of novels, or any of these things. But there is one activity where it's detailed, very detailed thinking along these lines, evaluations, and that's playing chess. Magnus Carlsen is a world champion. He was a world champion 5 times. After a while, he said, "This is boring," and he went to speed chess. Speed chess is called blitz. But you can think of it this way. In speed chess, you have an average of about 3 seconds per move. You've got to look at the whole chessboard and make a move in 3 seconds on the average. You've got clocks whereas slow chess is 3 minutes per move, roughly speaking. And so it's about 60 times slower. So if it's like running, there's no comparison. You're just going to have different people. But Magnus Carlsen is number 1 in both in terms of the rating. So this rating is an international society. Every major tournament anywhere in the world with top players is going to be rated, and it's going to be folded into the score that people have. So the rating might be 2,800, whatever, 28 and 35 or some such number. And it'll tell you how he has averaged, and it's based on how he does compared with other people who are also rated. So they come up with an overall rating. No bias involved. So you can look at the top players in slow chess, and let's say the top 20, and you can look at the top 20 in speed chess. Now, if we were looking at 5 kilometer, if we took the top 1,000 of each, there might be no overlap. That is 5 kilometers versus 100 meters. No overlap. But in the top 20 chess players, there are 13, last time I checked, which was August, there are 13 people who are on both lists of 20. Now, what this has to do with is it's basically saying the way you play slow chess is you get a quick impression. Maybe moving my knight to take his queen is a good move. Okay. And maybe you move that very quickly. If you might just move that, you only have 3 seconds. But then if you're talking about slow chess, you say, well, but if I take his queen, what can he do? And you're looking at different possibilities. He's going to checkmate my king and I'll lose the game. So I analyze this by putting together other quick judgments. Think of it this way. You're walking along a path and you come to a big puddle and there's mud on both sides. And you say, how can I get around this mud puddle? Well, you're looking around, you see some spots which look dry, or some rock, whatever, on both sides. And you're trying to say, does it look like I can get a path through there? My subconscious is telling me there are various spots that look good. And if I can chain them together into a path, then I can walk around the path. This is analysis. You see, this is conscious reasoning, but the subconscious is picking out the spots that look good. So all of reasoning is basically making quick judgments and then seeing if the judgments are good. Sometimes we just make the quick judgments without bothering to check. If we're walking along a path, we're not in tune with what our feet are doing. But if something unusual happens, then our brain starts paying attention. But most of the things we do are instant judgments. I was talking, a friend of mine called me up. He was stuck at the mall. I live in Columbia, Maryland, in the United States. And he says, I can't find my car. Can you help me out? And so I'm thinking, and I'm thinking that, well, I got to get my clothes on, get in the car, drive to the mall, then we're going to come some kind of a search pattern. And then boom, all of a sudden it occurred to me, on your key fob, there's probably a button. And if you push the button, the horn will blow. Because you have a Toyota, I happen to know. And so he did that, and the horn started blowing, and he found the car. Now, you understand the problem I was thinking about was what I'm going to do to get there and help him out. And instead, after 20 seconds, the subconscious had been calculating and came up with an alternate solution. I mean, I wasn't doing anything to think about the key fob, and boom, the answer pops up. That's subconscious. So what was my brain doing during those 20 seconds? And what is more important? The subconscious? The subconscious came up with the answer while I was consciously thinking about a different problem, namely how to get there and drive and so on. So I'm trying to say that the subconscious is the cook in the restaurant. He's subconscious. He's below your consciousness. In fact, you don't know if it's him or her or what. You don't know if there are 5 people or 2 or anything. And it's below your conscious. Therefore, you believe it doesn't count. And therefore, you tip the waitress. Now, I don't even have a way to tip them, but you recognize the problem that we're not recognizing, we're not giving credit where credit is due. And all kinds of our thinking is based on this. Again, subconscious can be trained. And many of the things we do wind up training the subconscious.
How?
So, well, if suppose I take a high school student, a senior, a 12th year student in high school, and this is a good student in math, above average in math, and I give him a problem, math problem, calculate some volumes, any kind of math problem that would be a standard problem. And then his subconscious starts thinking, aha, this looks like a quadratic problem. I have to use the quadratic rule. And I memorized the quadratic, it just pops up into his mind. And he tries to do it. And nope, turns out it doesn't work. Then he starts thinking, well, I should draw a picture. And then he goes through a conscious drawing a picture. He's going through various things he's been taught to do. And the subconscious is picking the ones which seem like they are most likely to work. And then he works through and he solves a problem. Okay? Now, his ability to do this depends on his ability to pick out the right algorithms to use, the right procedures. And so the subconscious is playing a big role. But basically, he's doing the same thing a computer would do to solve the problem. Namely, it tries to convert the problem as stated in English into a set of procedures it can go through to solve the problem. And sometimes people say that's not thinking. Whereas I say, well, you can't just talk about whether or not a computer can think without asking whether or not people can think. And if the high school student is going through the same procedures as the computer, then your definition of thinking must say that they're both thinking or they're both not thinking. It's either way. I mean, I don't care. But see, people spend 12 years solving problems. Did you spend 12 years solving problems in high school, through high school, from first grade through?
Mhm.
Yeah. How often were you just asked to create a new problem?
New problem. Never, probably.
Yeah. And yet, half of everything, when I talked about the economics problem of United States versus China trade, I say, well, let's create the problem of what's happening in the whole world. that's actually creating a new problem in a sense. You see, I'm changing the problem because I say that problem wasn't the right problem. A mathematician shouldn't just take a problem that's given to him or her. They should take the problem and figure out, is this the right problem? And if they don't understand where it comes from, they shouldn't bother solving it because it's probably the wrong problem. Okay, but so I convert the problem into what is the overall, if you add up all the countries in the world, is the United States buying or selling more? And that becomes a different problem. So I've stated a problem. Okay.
Mm.
And so anytime there's a problem to be solved, there are two aspects: creating the problem, answering the problem. Creating the problem, answering it, which is more important? Let's say they're equally important. Would that be fair? Now, if you're a student in college, again, you're not being asked to create problems. You're being asked to solve problems. And if you're in graduate school getting a PhD, by the way, a PhD, if you spend 40 hours a week times 50 weeks is 2,000 hours. 5 years of graduate school gives you 10,000 hours. That comes up with the 10,000 number I mentioned earlier, that if you're successful, you've spent 10,000 hours, not counting all the time you spent in college, for that matter, and high school and so on. Anyway, creating the problem is a big part, and the students in graduate school don't understand that. Now, I think the professors often give the students the problem to solve, most usually. So they're in some sense creating problems, but they haven't actually trained in creating problems. And well, they can say, well, here's a problem that's been pretty much solved, but we can change the problem a little bit and we get a new problem. So that's creating a new problem for the student. The student isn't good enough to figure that out on his own. But where the problem comes from is key. Now, if you are in competition with 100 people, we're all in competition in some sense in our fields of endeavor. And it can be a cooperative competition as well. We can help each other out. But if 98% of them are spending all their time on solving known problems, and only 2 of them are thinking about creating new problems, where is the opportunity for you? It's on creating the problems. That's the open field. I try to, when I was telling you about the genome problem, see, I'm saying here's a new area that people probably haven't looked at very much at all. And that's the opportunity. See, and sometimes you're wrong, and sometimes nobody ever cares about the problem. And sometimes it does become more important. But I don't study all the literature on chaos theory that I'm known for. That would be thousands of papers, and I just waste my time. I just try to look at totally new things I haven't looked at before, or how can I find problems that are where there are fields that haven't been investigated. And that's my approach. Finding the questions, and finding questions is a key perhaps the best scientists of the ever might be Albert Einstein. Okay. And he came up with relativity, special relativity, where we talk about how if a rocket is going at immense speeds, then time will slow down for the people on the rocket. He came up with the idea that gravity is actually bending of space. He came up with the one of the biggest things in physics is entanglement. And he came up with the idea with his collaborators that the idea of entanglement and the implications. He says, suppose we assume that such and such a rule is true. What are the consequences? That's the question. And what are the consequences? He says, so here's one. Now, James Clerk Maxwell from Scotland in around the year 1860 came up with our laws of electricity and magnetism. Now, that was a big deal because it is a much bigger deal now than it was then. Because in the 1800s, if people thought about electricity, it's, well, you get little sparks. And you walk across the store, when you walk across the floor on a rug, you may build up a charge and you touch the door and you get a spark. That's what electricity was. And now, and just compare, if that was your only contact with electricity, it wasn't very important. But he came up with these laws, and in 1860 and 1905, Einstein asked a question. He says, in Maxwell's equations, there are two numbers, and if you multiply them together, you get the speed of light. Now he says, this is very peculiar that there's a speed of light. And the theory of relativity, the word relativity means that speeds are relative. If you're in a bicycle race, you have a speed relative to the ground. You also have a speed relative to the person who's winning the race, unless that's you. Well, then this relative speed is zero. And all speeds are relative. Everywhere speeds are relative. Galileo knew that speeds are relative. Everybody knows that speeds are relative. So why is relativity theory called relativity theory? I'm not quite sure. But the thing is, the fact that there was a speed of light actually meant that everybody who measures the speed of light gets the same answer. So your speed, if you're sitting on the ground and you measure the speed of light, and somebody's in a train and they measure the speed of light, they get the same answer. So actually, the speed of light is not relative. So all of relativity is based on the fact that the speed of light isn't relative. And he said, well, how could that possibly be? There's the question. Is it possible to have a speed of light which is independent of who measures it? That's a question. That's not some famous problem that he solved. He created his own problem on something that was well known, these Maxwell equations. And he investigated it. And lo and behold, he came up with, well, if you're traveling in this, let's call it a spaceship, even though we didn't have spaceships back then. If you're traveling in a spaceship, maybe your time slows down. That could account for it. After a lot of thinking, this is not a quick judgment. This is a lot of analysis, type 2 thinking. After a lot of type 2 thinking, he says, well, time slows down in a moving body, which if you think about it, if I'm person A and he's person B, I see the watch on his hand as he moves past me. I see the watch going, and the second hand going slower than my own watch hand. Time is slowing down. His heart rate is slower, so on. And if he looks at me, he observes the same thing, that I'm going slower relative to him. And Einstein makes sense of this. It sounds like nonsense, but you can't have both of them. Each is going slower than the other, but each observes the other one going slower. And he came up with this by asking the question.
How do you ask good questions, and how do you develop the skills needed, to create a good, worthwhile problem?
Well, one of the things in mathematics you would do is you would say the only problems that count in mathematics are word problems, because that's relating things. And if you're always dealing with mathematics as in terms of equations, you often aren't given equations. So you have to connect. And as I said, the teachers nowadays give very few word problems because the students don't like them. I'm repeating myself here. And the reason people don't like them is because there's no procedure that they can crank out to answer a word problem. They've got to figure out what the problem is actually talking about. So that's the start. And to be an expert at asking questions, maybe it takes 10,000 hours. So we're not talking about quick fixes, but it's a question of asking questions. Asking questions that ChatGPT can't answer. ChatGPT is very good. All of these AIs are pretty good at answering questions. So what do you think of that?
I think what you're saying is fascinating. I'm struggling to understand how we can judge a good problem, the quality of a problem. Does time tell? Is it how much do other people think? Maybe your peers that are also interested in that topic, do they think it's a worthwhile issue?
Well, let me answer.
Yeah.
Let's recognize that this is a difficult question. Now, I have published about 400 papers in a variety of fields of science together. And some of them get a whole lot of citations. And that's my interest, is to get citations in the sense that I'm influencing people. They are looking at it, they're thinking that it's related to what they're doing. I want to influence people. The idea of publishing a paper is communication of ideas, and how many times they actually use this in some way. That's so you can look up in Google citations and find out how often a paper is cited. And so I have some papers that are cited quite a few times, and a whole lot of other papers which are cited very rarely. So I'm trying to tell you that maybe I'm not so good at choosing, but it's a question that occasionally I might be right at selecting a good problem. And maybe that's good enough, even with all my experience of trying to pick problems. Well, you see, you're trying to say, well, what don't I understand about this? And you start off with, what don't I understand about economics? What don't I understand about AIDS? And you try to, what do people in general not? Now, if other people understand it, then I'm not going to be able to write a paper on it. But if I come up with a question which I think people haven't looked at, then then I have something. See, that's
So providing impact to the world, if I understand correctly, for you is finding original problems and then spending some time on them, and some of them are going, in retrospect, looking at them, be more impactful than others. But it's almost like the important thing is you put yourself into that um, mindset of gonna find something in a field that's interesting and then explore it and try to create something. And in retrospect, we'll see how much impact it has. We can't really know before we start. Especially, it seems, with innovation in general. I don't remember the author's name, but I think you can't be. There's no structured way to be in, to you don't know the steps towards innovation. You kind of have to start from a bit of a
If you go
tell
through
us.
12 years of school and you're never asked to ask questions, you're never told to ask questions, then that's not a very good start for the game, right? I tell students in college, sit in the front row, which it tends to force you to pay attention. And you're not going to be looking at your phone if you're in the front row. And ask a question of the professor in every class. And you will probably have questions. And the sooner you ask the question, the better, because once you get so lost in a math lecture, you don't know what's going on. You can't even ask a question. But in all likelihood, some of the other students are also lost. And the question, when you want to ask a question, you're not asking a question, how do we apply this to some other field? No, that's not it. You ask a question is, I don't understand what you just said. That's the best question. What do you mean by such and such? That's the kind of question you start off with. So if you're sitting in a class, a question of, I don't understand, is a perfect question. I don't understand what you just said. Okay. So life is asking questions. And I keep asking with ChatGPT, I keep asking questions a couple times a day about things that I read something. What does this word mean in a context? And, when people look up things in the dictionary, which people don't do so often, but it'll give you several meanings and you don't know what applies to what. And so I came up with that word. Someone has an ischemic problem. And I put in, what does ischemic mean in the context of heart disease? Because that's what the article was about. And so it tells me. And so asking an AI is better than asking a dictionary because of you can tell it the context. And constantly asking questions. That's why I have a bunch of AIs, and I can ask the same question to two of them, like Grok, Grok. That's Elon Musk's AI. And life is asking questions. You have fewer answers than you have questions, so just start asking questions.
What are you currently working on?
I have two graduate students. By the way, when I talk about my work, it's always with a bunch of, at least one other collaborator and sometimes more. And it's a composite. The work is a composite. I just put in mind that these other people did as much as I did.
Mm-hmm.
And one of the reasons I can work on a lot of different problems is because I don't put in full-time effort on the problem, because they're also doing a lot of it. So if you took my number of papers and divided by the number of authors, and you get a much smaller number. So, by the way, I find that when I write a paper by myself, I just never finish it.
Interesting.
Okay, I can't explain very well, but but I get the energy to keep on going from my co-authors to say, where are we on this? And let's make some progress.
Interesting. Is it also s- social aspect almost, the fact that you
Sure,
can communicate.
sure. Now, the social aspect for me, is important. It's not a crucial step. I mean, for other people, they might be doing things on their own. I'm not saying that's a bad idea, but for me, um, I once found myself, I had a paper that was basically accepted for publication, but I had to fix up the references. And 6 months later, I still hadn't finished it off. And I said, I should learn from this about myself. Not that, hey, I should correct the way I behave. I said, I just said, this way I behave doesn't work. I don't have to change Jim Yorke. I just have to change my procedures of trying to work alone.
Mhm.
And if my collaborators are not in a big rush in getting something done, then it's neither am I, and it isn't going to get done.
Um, and I guess I wanted you to define in the beginning chaos, but I didn't want to interrupt the flow of the conversation. Um, so, what is chaos? You coined the term chaos in mathematics. I wonder why you chose that word.
Right. I wrote a paper with my student Chen-Yen Lee, uh, 1975, I think, and we titled the paper "Period 3 Implies Chaos." Now, then chaos wasn't defined. In fact, we actually didn't define it, but we talked about a mathematical situation which was pretty simple, and we were using the word chaos because it was simple to describe. I won't try here. Simple for a mathematical audience, and uh, but the behavior was very complicated. And chaos is a system which, in principle, if you knew everything about the dynamics, you could predict what it was going to do. There's no noise, there's no randomness. But if you're a little bit in error, then it can have a big impact. So chaos is where you can predict things in the short run because you have a certain amount of information, but in the long run, you can't predict. You can imagine um, you're going to go to work one day and you hop in the car and you're driving along, and there's a movie like this one, and there's a wasp in the car, and the guy swats it, and he misses the wasp, and the wasp stings him, and he goes out of control, and he crashes the car. Now you see, just whether you miss or hit the wasp is a tiny difference, and that tiny difference winds up in him crashing the car. Now, the way the movie goes on, he then continues on, and his wife gets worse and worse because he was late for work, and he gets fired, and his wife
Is this
leaves him.
sliding
And
doors?
sorry,
Is
no,
this sliding doors?
sliding doors is a very similar. That's very good, very good. Um, Gwyneth Paltrow is in Sliding Doors,
Okay.
and Sliding Doors is a Hollywood movie where somebody is going to get in the train car, the subway, the underground, and the door closes, and he or she, I forget, misses the train, and that the small difference here evolves into something which completely changes her life in a very negative way. And then they run the movie again, and she gets through the door on time, and her life goes on in a very favorable way. Same with the movie with the wasp, where they run the movie again, where he hits the wasp, and the wasp is dead, and he doesn't crash the car, and his life goes on. And so little changes can make big differences. Okay. Now, I have prepared for this question. You didn't say you were going to ask me this question, but I'm taking an opportunity here. Okay. I have a device to show you.
Mm-hmm.
Okay. Many years ago, a graduate student in physics, Troy Shinbrote, made one of these double devices as a double pendulum. And it exhibited a lot of chaotic behaviors. And now he's full professor at Rutgers. And I'll show you one of his double pendulums. Let me okay, here we go. I want to try to figure out where. See, this is a pendulum. There are no motors or anything. It's a pendulum, and below the so the blue is a pendulum, and the silver one is a pendulum.
Mm-hmm.
Actually, it's not really made of silver; it's made of aluminum. But silver is a fancy word for aluminum. Now, you see, you have these different kinds of simple behaviors. And see, the pendulums are both swinging at different levels. It's kind of a little funny. You can see there's something funny about their movements.
Mm-hmm.
And the blue one is plastic. But you see, it's pretty regular behaviors, and you can find the equations of these double pendulums in the books going back to the 1920s. But if we give it a swing, that's a completely different behavior.
That's so cool.
Yeah. See, it does one thing and then it stops. Now, has it stopped? No. You think it stopped and it hasn't. So this isn't really chaotic because it eventually runs out of energy. But in the meantime, you can see it's got very complicated behavior for a simple device, and it's complicated. It's doing one thing and then it seems to be doing another. Your eye can pick up this difference. So this is when Shinbrote showed me this, I said, this is an outstanding guy. Go on his own and build this device, and he became one of our graduate students. Now, this is about predicting the future. Okay. And I'm going to invite your audience who's listening to participate and compete. Who can they compete with? They can compete with Kriakos. Okay. Sit back a second. You sit back, get your hand off your face. Now, clap your hands in front of your face. Okay. That's your way of communicating that you think the pendulum has stopped flipping. So what we saw was that the blue pendulum goes through 360 degrees. It flips through. And I want you to clap your hands when you think that it has stopped going through. Okay. Now, that's already stopped in that sense. But if you're wrong and it goes through, you get to play again. And if you're wrong, you get to play again. You can clap your hands as many times as you want, but if you don't clap your hands and it stops, then you have lost the game.
Can we play?
Yes.
Let's do it.
Okay. The game is afoot. You notice how often the blue one switches directions.
Wow.
Sometimes it's going clockwise, sometimes counterclockwise. And basically, a tiny change in how I start it totally changes the behavior. And I have never gotten very good at predicting this thing. So
I need the class.
Now, right now, some of your audience, okay, you've clapped.
I think I clapped too late.
I think you have done very well at the game. Okay. Now, see, chaos is about situations which are sensitive to small changes, like you playing billiards or rolling a bowling alley. Uh, Small changes in the behavior of the ball makes a big difference in what happens. And life is like that. And we know that we know that life is full of surprises, positive and negative. And uh, so that's my demonstration of what chaos is. And in the same sense, person driving down the road and the wasp, this is a small change in the system as to whether he misses or hits the the wasp. That's pretty much what life is like. I once had a woman come up to me after I'd given a talk, a while after I'd given a talk. She says, well, she couldn't get to the actual lecture, but about chaos. And because her both her bathrooms were out of operation and the plumbers were there. And I told her, wow, but she understands chaos. Everybody understands chaos, but she understands her life is chaotic with plumbers. You don't know when they're going to show up, and you don't know if they're going to fix it. And then the kids are entering in the problem, and how do they go to the bathroom, and a lot of complications. And that's what life is like. And that's what I meant by saying that this kind of device here, this device is chaotic. Whatever you see here, that's what chaos is mathematically. And the word chaos is an old word, and people, so there's one use of the word chaos which is not typical. And that's in the Bible, and it says, in the beginning of the Bible, it says everything was chaos. I don't know the exact phrase, but that's everything is totally, absolutely unknown. That's a different kind of chaos. That's not what we mean by chaos. What we mean by chaos is uncertainty in a bounded way, like the woman with the bathroom with the toilets that were plugged up, and the plumbers that might or might not be coming, and all these things are bounded chaos. It doesn't mean that all of a sudden the Earth is going to shift out of its orbit and go to Pluto, or it means within bounded constraints. And so this thing here, the pendulums are clearly confined to a limited region of space, limited speeds, and it's limited chaos, but it's unpredictable. Okay, so chaos is things which are predictable in the short run. So, for example, if I was to say, I'm going to let this pendulum go, you can see that it's going to start off by going down. So you can predict it in the short run, very short. And in the long run, you can't. So that's what chaos is. And everybody has known about chaos their entire lives. So what I was trying to say is that this mathematical thing we're seeing here is what people ordinarily mean by chaos. It's a representation of chaos. So it became a standard term in mathematics, which was not our intention. We had no idea. Let's see the impact. Period 3 implies chaos, the title of a paper. It's an unusual title, but no way did I think that people would adopt the word chaos as the name of the field, chaos theory. But they did. Now, the Russians were a bit ahead of the West in these theories, and they had a term, stochasticity. And that's not a good term because stochastic means some kind of real randomness. this thing isn't random, because we've seen that if we know its position, we can predict its position soon afterwards. We just can't predict it for very long. And the Russians switched terminology and they adopted the word chaos, totally to my surprise. So, I mean, who would have thought that they would change an established term? And so that's chaos theory, looking for simple situations which you can appeal to people with general interest. So this is a chaos machine, thanks to Troy Shinbrot. And you can go on the web and you'll find lots of double pendulums. I mean, we've been doing this for 20 years, so it's caught on, and many people will be showing double pendulums. I like to say we use the up in the top, we use ball bearings, uh, the highest quality roller skate bearings you can find.
Interesting.
Okay.
So how do you what you've given me the example of the newspaper, but let's say I've come across something and I wonder, does this exhibit chaotic behavior? What's the next step? How do I go on trying to see if there's actual chaotic behavior exhibits it? Do I start making a graph? What's the concrete next step?
Well, it depends on what we can do, of course. So what I was saying here is we can simulate this mathematically. And I was saying we can start for this condition, initial condition, and see how it behaves. But now that's not chaos. Let's change. Look at the angle of the blue and the silver. I'm going to change that angle a little bit, or maybe sharper angle, less sharp angle. Make a tiny change, 1 degree change. What happens if you look at the different solutions? If they behave differently, quite a bit differently, then we would say it's chaotic. So a change in initial conditions of a small amount makes a big difference. Okay. So you can predict, if you don't know the angle exactly, you can predict what's going to happen for a while. It's going to start falling down. I don't know exactly what they're going to do. You're going to be able to predict that. But once it starts spinning, once this thing comes up here and nearly goes through and doesn't, or does go through, well, in any case, does or doesn't go through, that's that then it becomes really unpredictable after that. I mean, you have no idea what it's going to do.
How do you so for this in this example, the angle was a variable. How do you identify all the variables? In this example, I wonder, like, does the density is it the density of the material a variable? Is
Okay, so
the
first of all, there are different kinds of variables. So what are the varying variables? The angle up here of the silver one, that is a varying variable, right? And you've got another variable value, which is the angle of the blue one. And you also have the speed of the silver one and the speed of the blue one. So you've got 4 varying variables. Okay. Then in addition, you have the friction and the mass. Now these are fixed variables that don't change that they're fixed for this particular device. So there are a bunch of these, such as the masses and the force of gravity, that's fixed. And so if you look back in the 1920s and you find these equations, or you go on the web and ask, what are the equations of a double pendulum? Or ask the AI, what are the equations of a double pendulum? And you will get answers, and it'll be certain constants, and you have to figure out what the constants are. You could do that through various experiments. But so in principle, you could do your best to come up with the friction, but you might have an error in the friction of 1 or 2%.
What about, let's say, I have an outside world problem. Maybe it's the weather, maybe it's a population of different species, and I'm trying to see how do these population levels affect each other when there's a decline or increase. When there's so many variables, how do you pick up on the important ones, and how do you
One reason
yeah.
I got interested in epidemics is because it's population biology. But when you read papers and they say, well, you can see cycles. If you look at the wolves and the deer, not sure those were the species in Canada, and the trappers would collect the furs, and you could see oscillations from year to year as to how many furs they collected. And I say to myself, that's a terrible set of statistics. How can you believe anything from this? If you want good statistics, how are you going to find out about thousands of individuals? Well, with epidemics, you find that you're talking about hundreds of millions of people. And you're getting statistics on a population of 100 million people. And so this is population dynamics. And so so when we got this, since I had been working in population dynamics, I was aware of the idea, that is, I'd been working in epidemiology, mathematical epidemiology. I was aware that when the big epidemic broke out, that in 2020, that something was afoot. I mean, something really big. And there had been a number of previous episodes where something had almost broken out in the last 20 years. There was a Mexican flu, and then there was a Hong Kong event which was SARS. And these didn't really turn out to be very big epidemics, but they were alerts. It's like somebody shoots at you, and in the first 3 times they shoot, they miss your head. Do you say there's nothing to worry about? No.
There's plenty to worry about.
But people say, oh, these epidemics don't turn out to be anything. Well, did you buy N95 masks?
Yes, I have some in my wardrobe.
I bought my N95 masks from the 3M company 5 years before the outbreak. I said, what can I do? If there's going to be an outbreak, and big chance, it doesn't have to be even 50%, but I think there's a big chance there's going to be. I'm going to go out and buy these masks. And you buy rubber gloves. They never came out to be very useful, but I bought them 5 years ahead of time. And so I had plenty of boxes of N95 masks. And I was recently talking to somebody. He brought up the fact that I gave a talk at the University of Maryland, and in March of 2020, and I was talking about how bad this epidemic is going to get, and it's going to close things down. And he told everybody in the room thought I was just crazy. I mean, look, we're going to school. I mean, there's nothing unusual going on. Yeah, in China there's an outbreak, and what I saw was that, according to the web, the number of cases was increasing by a factor of 10 each week, and had been going on. And let's not ask whether or not those were correct. This is the best data we had. And if it goes up by a factor of 10 to 100 to 1,000, in 3 weeks, it goes up by a factor of 1,000. Another 3 weeks, it's 1,000,000. Another 3 weeks, it's 1,000,000,000. 9 weeks, it hits everybody in the world. And that's a mathematical model. What happens when things go up by factors of 10 every week? Of course, it saturates the population at some point. And I was telling them, this is what's going to happen. I was telling, in January, went to visit some people in Texas, and I said, we're supposed to come back in April, but we're not going to be able to come back in April because of the epidemic. And they said, what epidemic? And I told them, well, this thing that's breaking out. And we knew in January that it was going up by a factor of 10 each week. And so you figure April, that's 3 months. You're not going to get to April without a big outbreak. You're going to be locked down. Now, this is a mathematical model. And the newspapers are very careful at not challenging the thinking of the reader. Exponential growth. If you go to the economics page, you'll sometimes find plots which are on an exponential scale. So it goes 1, 10, 100, 1,000, and you can see how things behave. But on the front page, they'll never put an exponential scale. That's what you want with epidemics. You want to see the exponential growth. And this is just thinking about these simple ideas. See, when I was in high school, I read about Einstein, and I read the stuff that a high school student can read. I'm not talking about advanced physics or whatever. And I found that he was looking at different kinds of problems at the same time. And so, let's see. He talked about light, the speed of light. It's an electromagnetic wave. And he says, if we accept this Maxwell's equations, then we wind up with a completely new view of the universe where time, we are going to overthrow Newtonian physics. Newtonian physics had time being the same for everybody. And so Newton was published his results 1660, 1680. I forget. I think in mechanics was actually published in 1680, roughly. And he overthrows Newtonian mechanics. Now, if you overthrew Newtonian mechanics, something everybody had accepted for 300 years, 200 and whatever, then you'd be pretty careful about it. What does he do? The same year, he publishes a paper that light is a particle, or more or less. Same year, he overthrows Newton based on the idea that light is a wave, and now he's writing a paper about light being a particle. How is it possible for one to fit in one brain in the same year, the contradictory ideas? And he was able to do it. So actually, he got a Nobel Prize for this particle thing. So Max Planck had come up with a paper, and he says you can explain certain well-known data only if, it's been unexplainable. You can explain why you get these formulas. He said, if you assume that when light is emitted, it's emitted as a particle of energy, an amount of energy. The amount of energy that's released is proportional to the wavelength. So that ultraviolet would have higher energy than infrared. And he came up with this idea that light is emitted as a fixed pulse. Now, Einstein had a different problem he wanted to look at, and it was that when light is shined on a metal, sometimes electrons are knocked loose. Electrons had been discovered a couple of years earlier, but you could measure that electrons were being knocked loose. But only if you had a high enough frequency light. So if you're shining, let's say, you might find that if you shine ultraviolet light on it, no matter how much you shined on, a little or a lot, some electrons are being knocked loose. The brighter the light, the more electrons. But if you shifted to infrared, no electrons were loose. No matter how much infrared you shone on this metal, it didn't come loose. And Einstein said, well, let's just see how this principle of Planck can be applied. He says light is emitted in discrete packets. What if it's absorbed in discrete packets? Isn't that almost the same thing in physics? You look at a video of the solar system moving around, and they're following Newton's laws. If you run it backwards, they're again following Newton's laws. You can't tell which one is the original. And so if it's released in a packet, the opposite of that is, time reversal is just it's absorbed in a packet. So if you had enough energy, it could knock loose an electron. The packet could knock an electron loose. Okay? And he says, let's assume that what he says is correct, and we just reverse it and reverse time, and we get this. So it's being discrete packets of light. And he got a Nobel Prize for this, by the way. That's what he got the Nobel Prize for. Okay? So
sorry to interrupt you. Please continue.
So what I'm saying here is that he's taken a completely opposite point of view in the same year. And to me, this is what I was learning when I was in high school. This was his approach to science. And he would ask a question. People proposed laws of quantum mechanics. So he was the first one to believe in quantum mechanics because of this particular experiment I was describing. So I think, well, look, obviously I'm not going to try to be Einstein. I'm not that bright, but nonetheless, you can ask. I don't want to focus on one area. I'd read science fiction stories about how sometime in the future, there's this fellow who comes along and he's interested in a lot of different things. And all the scientists are focused on very narrow areas. And by making connections between these areas, he can have a huge impact. And that's a science fiction story I read back in high school. And that's basically my way of thinking about the world, scientifically.
It reminds me of Schrödinger's preface in What is Life, when he says, sometimes people have to attempt to go into fields they are not very knowledgeable on and apply what they've learned in their fields of specialty. And so then he says, in this book, I'm going to attempt to apply what I've learned in physics to biology, and perhaps I'll make myself a fool in the process, but so be it, which is one of my favorite parts that's my favorite preface in a book. Yeah.
Okay, let me give you my quote. I tell people this all the time. You have the choice of looking stupid or being stupid. And if you're a student, remember, you're sitting in the front row, you're supposed to ask a question. I might look stupid. You have your choice. Look stupid or be stupid. If you don't ask the questions, you're going to be stupid. You ask questions. I tell the stupid questions are the best questions because it's most likely that the most people have the same question. And so you're in a class, you ask a stupid question, and all the other people are feeling stupid too. I think it's and so Schrödinger is talking about becoming public with your ideas. And so I agree. But it's not just when you go into a scientific field. I'm saying it happens every day when you're a student and you're in class. You have the opportunity to be stupid all the time. and you want to overcome that. In fact, I try to stimulate questions when I go to a seminar. I try to ask a question very early in the seminar in order to start the avalanche of questions of the other people. People tend not to want to be the first person in a silence of the audience. But once you ask a question, other people start asking questions. So it's a service to ask a question early in the game. I remember one time I was a student, I asked a question. I was so nervous asking this question that I couldn't tell whether or not this question actually hung together in English. I just remember this feeling. Did that make any sense? What I said? And the professor answered the question. So I guess it made sense. But I'm not saying I'm not nervous. I've gotten less nervous with time. But yes, you're going to be nervous asking questions. You might look foolish. You're going to be nervous. Put up with it. Ask the stupid questions.
How do we better the education system? What steps need to be taken? We've talked quite a bit about education today. I mean, you've talked about students being encouraged to ask questions, students creating their own problems. Is there other things that would make the education system better?
When I was in high school, graduating from high school, I wrote to a professor at Columbia University where I had been accepted for the next year. And I said, I wanted to get into such and such a class. And he wrote back and said, well, you have to read this book by Paul Halmos. So vector spaces. So I got the book, and Halmos says in the very beginning of the paper, of the book, something about how you have to challenge yourself. That is, you have to learn all the theorems, but you can't just read them and try to memorize them, because that's not making your brain work. You've got to figure out how would you come up with these answers. You have to challenge yourself. So if you try to prove it by yourself, and if you can't prove it by yourself, then you read a little bit of the proof and say, what comes next? And try to fill in the blanks. And you keep on doing this, and then you read a little bit more. And so you find out, see, if there are 10 steps in the proof, to you, they might like that they're all reasonable steps. You can follow through it. But how did they come up with the 10 steps? So you have a chance by not looking, by seeing what those steps are, like one at a time, bit by bit. I had a job summer job working at a tuberculosis hospital. I was in the laundry, and I would take a long bus ride each way. This is in the summer before going to college. And so I'd be reading the book back and forth. And so professor wound up letting me in the class. But I understood from the beginning that it's not just a question of absorbing the material. The question is understanding how you come up with it. How did they come up with this? How did they come up with this? That's the constant question. Now, the material has to challenge you. It's not just a pianist learning the notes. They have to teach their fingers the sequences, shall we say. They have to make various kinds of patterns, type 1 patterns, system 1 patterns, which they can recall quickly. And questions such as Einstein asking, how is it possible for something to have an absolute speed? How is it possible? And um, and the answer might not be forthcoming for quite a while. In another one of his papers, he said, if you're in an elevator and you don't know where the elevator is, and you can feel yourself standing on the ground with 1 g of acceleration, I mean, it feels like regular gravity. There are two situations where you could have this. One is you're on the ground and you're getting 1 g of acceleration, or the other one, you're out in outer space where there is no gravity and you're being accelerated. And he says acceleration and gravity might be the same thing. What if they are exactly the same thing? And he said, so this is a type 1. I prefer the term type 1 to system 1. But type 1 type of question. It's a basic question. And where did it come from? Who knows? He said this was the happiest thought he ever had in his entire life. This question, finding this question. And it took him years to come up with an answer. So asking questions. What don't you understand about this theory? I was working with a high school student and she was studying, I had her studying white dwarf. So it was quite advanced, but I wanted her to study in great detail. And so we went through the whole theory. I made her do it because my idea of teaching is, well, classes last 50 minutes and they're 3 times a week or 5 times a week or some such pattern. And we're always taught the way you learn things is you sit in the class for 50 minutes and absorb what's there. This is not how you learn in life. Once you're out of college, you're not going to find 50-minute classes on what you want. It's a bad model for education. The right model for education is you find out the answer yourself. You go on the web and you find out your answers. And you constantly do this. And AI makes it significantly easier. And don't trust what the AI says. You get ChatGPT, it says, let's go to Grok. Ask the same question. Just paste the same question into Grok and see what answer you get. And see if it's the same. And so it's a question of asking questions. And now we have this tool, which is even easier to get answers. Okay. So it's asking questions. You make a life of asking questions. And some might be more interesting than others, but basically, we're all pretty ignorant compared with an encyclopedia.
And I have a friend, Finn. Finn studied neuroscience and now he works in medical technologies. And we were reading last week, we did a book review on Donella Meadows' book, Thinking in Systems. We chose that book because...
Wait a second.
Yes.
Now, let's focus on this.
Yes.
I want your audience to understand something here.
Yeah, of course.
Now, we have not discussed this topic at all.
Yes.
Thinking of systems. Let's see. This may be a complete failure, but let's try.
Oh, that's so good.
Now, the question I'm going to ask is the book. What is the book? The
Thinking
title?
in Systems.
Okay. Ready? I'm going to...
Yes.
Hello, Grok. Tell me about the book, Thinking of Systems.
I think you mean Thinking in Systems by Donella Meadows. It's a classic on systems theory, breaking down how complex stuff like economies, ecosystems, or even your daily routine interconnects. Meadows explains concepts like feedback loops and leverage points with clear examples, no jargon overload. Want a deeper dive on any part?
Well, what is a system? See, I want to follow up with questions. So my follow-up question is, what is a system?
A system is just a bunch of connected parts working together toward a goal, like a car engine or an ecosystem. Every part influences others through inputs, outputs, and feedback loops. Got a specific follow-up about it?
Yeah, I see. The idea is to keep asking you questions. And so my question is, what's a goal? What are examples of goals that you used the word goal?
A goal's the purpose or outcome a system aims for, like keeping a thermostat at 72 degrees or a forest maintaining biodiversity. Examples: a business hitting sales targets, your body regulating heartbeat, or a team winning a game. What's your next question?
Is the world a system?
Absolutely. The world, or Earth, is a big system with parts like atmosphere, oceans, people, all interacting through cycles like water or carbon. Think climate patterns or economies tied together. What else?
I'm going to stop. Okay.
I think if this is, I think I need a copy of your AI conversations and just study them.
Okay. So what I'm trying to impress your audience with is that there are these, you can ask anything about, don't ask predictions about what the stock market is going to do. It's an encyclopedia. It's a very intelligent encyclopedia. It's going to tell you about the facts. It's not going to predict. And furthermore, don't trust what it says. We can go to another one of these AIs and ask the same question. By the way, was it loud enough for you?
Yeah, no, it was good.
So I want your audience to understand they can ask questions about anything within of an encyclopedic nature, see? And these are not always up to date. So how old was this book?
Meadows, it's been at least 20 years, I'd say. I might be wrong, but I think that's what Finn said. Can Google it.
I will show you also. Let's see if I can get this camera to focus on this. See, it gives me a printout of everything we just talked about there.
Mm-hmm.
So,
Mm-hmm.
Okay. So, I mean, everybody, look, this AI idea is coming down the pike, down the highway towards us. We have to be asking it questions to stay relevant. I'm trying to bring up the question in the math department at the University of Maryland. And I say, look, are we preparing the students for the future? Well, mostly they're worried about the fact that if they give a homework assignment, the students will and do feed the questions in to the AI and it'll give them answers. And then, so they're cheating. So how did the student, if you don't do homework problems, that's the way we challenge ourselves is by doing homework problems. And if they're just feeding it into AIs, then that's a big problem for the procedure for learning. I don't have an answer to this, but what I'm saying is the most important thing to do in life now is to master the AI. And you don't, and there's this idea that you can ask just the right question. There's an art to asking the right question. No, what I demonstrated to you was you ask a series of questions. So for example, you might ask it something and it gives you an irrelevant answer. It may be misspelled. You misspelled something even, but they said, no, that's not what I mean. I mean something else. Your real goal in dealing with the AI is to control the AI to do what you want. That's not always easy. So this should be your goal for the next 5 years, the next year, the next month, the next day. Getting control of these AIs, not a particular one, but learning how to deal with them. Because if you were to hire somebody and they had this ability to go and ask all kinds of questions, and well, you're having trouble with your camera isn't focusing. Let me go on the AI and I'll find out what the problems might be. And you have to talk about the focus of the cameras and oh, here's a camera which is particularly good at that. Okay, I mean, so you'd hire somebody who knows how to deal with the AIs. And companies are going to want to hire people who know how to ask AI questions. not a single question, but a series of follow-up questions.
Interesting. What do you do in your free time? It's a hard one. It's a hard one, free time, because I enjoy most of the things I do. So for me, I wake up and I'm like, great, this is like all days free time. But what do you do outside your work in mathematics and chaos? And
Well, let's look at a slightly different point of view. Yesterday, I got on Zoom at 9 o'clock in the morning and talked to some students at the University of Maryland. And then at 10 o'clock, my Japanese collaborator came onto the call, and so we talked. And then the students left. And then I talked until noon about the problems that we're working on, which is basically problems about AI and determining where the genes are in the human genome, where a lot is known, but not enough. And so can you use an AI to answer this question? And then at noon, I switched over and I had a 2-hour conversation with 2 people in Italy who I'm working with on just some kind of a mathematical situation. And that involved some computer programs. And I was demonstrating to my Italian collaborators how you can get the AI to write your computer programs for you, which they were not aware of. And when you're doing it, it's like they speak English. I told it to speak English, not Italian. And they were amazed at how much it just acts like a person you're talking to. And it understands the problem. I explained to them, you take your existing program, put it in, and it'll tell you what that program is doing in terms of language which isn't in the program. It understands what you're doing. And okay, that was 2 o'clock. Then I went to the gym, and I have a trainer a couple times a week where the trainer makes me do a variety of exercises. I try to excel and strain, and because having muscle matters when you're. So I'm 84, and I want to be able to continue doing things. And I got back home. Right now, we've had a snowstorm, which is unlike any I've seen before, where there's about so much snow, but the top of it is ice. And early on, if you stepped on it, it would break. Now it's hardened up, so you can walk on this ice. It just looks like snow, and yet it doesn't break. And so one has to be careful when you're out walking up to the athletic club to for me to see my coach. But the idea is to see if you can excel and strain yourself. And the purpose of the athletic trainer, well, he tells me what to do, but also he keeps me doing. It's like teachers not only teach, they also set a clock. Your homework is due tomorrow at noon. Okay, so this is setting your pace. And without having a pace, I told you when I work by myself on my papers, that the papers never get finished. So having a clock set, a deadline, is important to everybody. And the teachers are providing that, and the coach is providing it. And then I'm listening to an audiobook. My wife and I had some kind of chili with a lot of beans in it, and we made we heated up. We had the same thing yesterday, and so she had made the beans, and it's made the chili. And
who's the better cook, you or your wife?
Well, you see, when with all this ice around, it's a different story. But I often get dinner, but I go to the stores and buy it, and bring something home of interest. And sometimes she makes. I'm willing to cook salmon 3 minutes on the side in a frying pan,
Nice.
and or a steak, 3 minutes on the side in the frying pan.
Do the same thing.
And so I did the dishes.
Nice.
So I also was listening to a novel and on an audiobook. So
Which novel?
which novel? So it's a new book, quite new, called Pendergast: The Beginning. Pendergast is an author. Sorry, Pendergast is a character in a series, and he's a weird type of guy, and so um, this story tells about Pendergast's beginning. It's by Preston Child and what am I saying? It's by Douglas Preston and Lee Child, and the, what I'm reading, and this one is good enough that I really want to, you want to find out what's going to happen. I mean, they're different. When you read these novels, you're at different levels of how much you really want to. You can't put it down, and so this is sort of at that stage of hard to put down.
So when I try to understand what makes a person innovative, what makes someone come up with great ideas, I try to understand their life holistically. That's why I'm asking you things outside your work too. I'm trying to paint the picture. Um, is there something that you do that helps you and gives you clarity of thought? May it be meditation, maybe going for long walks, or something else?
Well, according to my readings, and by readings I include YouTube videos, uh, exercise is excellent. Okay, and one of the things I'm interested in is the difference between type 1 thought and type 2 thought. And how can we train our type 1 thought? And so I'm going to go back to that same microcosm of thought, which is chess. And I go to chess.com and I ask it for puzzles. And so I may look at this puzzle for 3 or 4 minutes trying to solve this. What's the sequence I have to move to win this game? And so my brain is suggesting several possible moves. These are the system 1 ideas. I'm exploring different avenues of approach. Oh, should I move the knight or should I move the bishop? Or maybe I should move the king. So each of these is a separate branch of the tree. But the type 1 system in my brain is providing these. Well, think about the king. Look at that king move, maybe. And then you got to explore that with your system 2. I am trying to listen to myself working in system 1 and system 2, type 1 and type 2. That is spontaneous and versus analytical. And they go together. And my goal should be and is to improve my ability to work at chess puzzles. This may have nothing to do with my ability to play chess because sometimes the puzzles are very artificial. Any case. So I'm trying to understand system 1 and how do you train system 1? I say there's an actual third system. System 1 and system 2 are for what you do in a short period of time. But what you're also doing is you're trying to train system 1 and system 2. That's what system 3 is. Your procedure for playing, right? For learning. And so you solve a puzzle. It could be a math problem. So I would tell the math professors, tell your students repeatedly, when you solve a problem, it takes you perhaps half an hour and you've got a bunch of problems to solve. Don't just stop there. Go back and ask, what have I learned? What I learned that the way to solve this problem is a certain set of ideas. Why weren't they the problems I started with? Or why weren't they the methods I started with the wrong approach or something I didn't understand? What did you learn? Just look at that idea. It should become a system 1 idea. So it should become, you want to make whatever you were doing wrong to be forgotten, and you want to make this a system 1 approach. And you do that every time you have a homework assignment, and they're all going to say, I don't have enough time to do that. Well, then you don't have enough time. I tell people all the time, you have your choice. Do you want to be a student or do you want to be a researcher? And if everything you're doing is making yourself into a student, then you're not going to be a researcher. You think you are. My niece told me her son skipped 2 grades in math in middle school. And I said, oh, that's terrible. And how is he doing in math now? Well, he doesn't enjoy it very much anymore. Anybody can be accelerated to the point where they are mediocre or worse. And that's not an advantage. What's really an advantage is for you to understand the basics in a better way. Not to understand more things at higher levels, but to understand the basic ideas. Well, without writing down...
How do you do that? How do you understand the basic concepts in a better way?
You want to understand, well, in chess, I go back and I try to look at, and well, now I can see that that move of the king was interesting. It's not the first thing that came to mind, but now I can understand why it fits in. So you want to figure how these things fit together. There's a, you want to solve a quadratic equation. You have a certain formula. That's kind of that work. Another one would be if the Pythagorean theorem, where if you have a right triangle, the sum of the squares of the lengths of the short lengths, this is the short length, this is the short length, is equal to the sum of the squares is equal to the square of the length of the hypotenuse. This is the hypotenuse. Okay? You want to understand that better. Einstein came up with a proof when he was 12. Just imagine coming up with your own proof of the Pythagorean theorem, and really it's a very nice proof, but we don't have a blackboard here. Can't show you the proof. And so he understood the Pythagorean theorem better than anybody else. Now,
Very useful.
Wait. Now, he also came up with relativity and how time slows down. How much does the time slow down? It turns out you can draw a right triangle, and this is light traveling here, and then from the other view, it's traveling here, and this length is the amount that, so this is length 1, and this length is the amount that time slows down. That Pythagorean theorem, I don't want the people to follow me in detail here. The idea is that the Pythagorean theorem is the theorem for telling how much light slows down by. That's the first thing you're going to do in relativity is figuring out how much time slows down. And he happened to come across this. See, he asked this interesting question, and he came up with an answer. Nice that it's got both, otherwise he wouldn't have a theory. But it immediately comes, I shouldn't say immediately, he comes to the question of how much does light slow down by, and it's something that he investigated when he was 12, but in a different context. He understood the Pythagorean theorem better. It was really ingrained in his brain in a better way. Now, that is a remarkable fact, and maybe irrelevant. Maybe it's irrelevant that he did this. But to me, okay, here's another one. Your older clientele will remember that Bobby Fischer was the best chess player in the world some years ago. And here's a peculiar fact about
Sorry,
him.
I'm going to interrupt you. My dad is going to love you for all of this chess talk because he loves chess.
Okay.
Sorry, please continue.
Yes. Now, the story is that he learned to play chess when he was 6. It's a good age to start if you're going to be a chess master. His sister taught him how to play, but she didn't particularly like it, so she didn't play him. And he didn't have anybody to play. So for 3 years, he played chess against himself, making moves for the white and the black. Now, imagine wasting 3 years of your lives without knowing that you're supposed to do certain things like take over the center, and you worry about knife forks where the knight can attack 2 players at the same time. And you're not told these basics, and he's got to learn it by himself for 3 years. He wasted 3 years of his life on the very basics, and then became world champion. Okay? So there's got to be a connection there. If you're just doing everything you're told, okay, check for knight forks and move your pawns to the center of the board and castle your king quickly, and you're following these rules. See, you're not learning it at the level that Bobby Fischer learned it at. He learned it slower, but better. Okay? And Magnus Carlsen, who I've mentioned, emphasizes over and over again on YouTube that he's an intuitive player, that he doesn't really think in terms of looking at long, complicated chains of moves as much as compared with other people. He's more intuitive. He's just looking at the right move at the right time. And of course, he does look at combinations, but his emphasis is, without his mentioning it, it's type 1 thinking for chess. And so you have to train your type 1 thinking. And everybody, I mean, look, I think if you go back to the Greeks, they're going to tell you that asking questions is tremendously important. And so it's not a new idea. But there are places where you really can't ask questions. You're not allowed to ask questions. So I should also say that when I studied mathematics, I would take courses in the winter, springs, fall, winter. In the summer, I'd read a book. And when you're in a math class and they're going at a certain speed, and you start thinking, well, what happened up there at the top of the board? And then the teacher's going on, you're losing track. And so if you try to think about what's going on, you can't. There's no rewind. Whereas if you can rewind it 10 seconds, so what did he say? I still didn't catch it. Rewind it again. And the ability, reading a book on your own or doing a lot of rewinds, gives you time to think, and it allows you to go at your own speed. And so if you're trying to think a little bit deeper, you're going to be thinking slower. And reading a book over the summer, a math book, not with the goal of getting through the whole book, but just one page at a time, just trying to understand what's going on. Don't try to rush it, just try to understand it. And some of it you don't understand, you keep on going on, but mainly you're going at your own pace and you're rereading each sentence as many times as you have to. That's the way. And so I learned stuff better that way than by sitting in class.
I can relate a lot to this because I get lost at lectures quite a bit, and then I realized that after my first exam at university, and since then, I go to the mandatory lectures, and besides that, I stay home for quite a few hours every day, and I put a timer on, and I just study by myself, and I open ChatGPT's voice chat, and I just chat to it for hours at a time.
Great.
And I just see my PowerPoint material, and I just ask it questions, and that's extremely helpful, and that's how I pass my exams. But yeah, now it makes sense what you're saying. I've never thought of it like that.
So sit in the front row and ask a question every class.
I
Now,
feel
if you
I
you
have
may
to.
have
I have to.
just when asking the
Yeah,
question, you
yeah,
might
yeah.
have to wait till the end of the lecture in some cases.
Yeah.
But try to get that question in.
I have to develop this. I'm good at when we have small group sessions. I ask lots of questions. I don't worry about looking stupid. When there's 200 people in the lecture theater,
That makes it more difficult.
I feel almost like I'm taking people's time. I shouldn't be interrupting, and then yeah, it's a little more difficult.
Now, well, say I'm thinking more of a class of 20 or 30. So
Yes. And I do love those classes more because I can actually learn more. So
okay,
that might be the reason. The fact that there's more questions, more dialogue.
yeah. So all of my message that I'm trying to give you here on the various messages, there's nothing new here. I'm just trying to give you a different emphasis. In particular, the idea that your intuitive reactions to things can be trained, and you know that, and that it's more important than the analysis part, because you can't walk down the street without using your intuition as to how to walk. It's a learned thing, and you learned it as a little kid. So again, when you've done these homework problems, you go back over it. Now, another way to do this is to help a younger student with math. And by doing this, you will be refreshing your own memory of the stuff you studied the year before. And you'll actually very easily lock into a better understanding of it by refreshing your own memory. Or just take out the problem sets that you solved the year before or the semester before and just look them over and see if you can remember how to do it and try to do those problems over again. It should be faster this time. But you were supposed to gain something from that. So often students think of a class, the class ends, you got the final exam, and that's it, I can forget everything. I mean, I've heard people say this. It's just kind of weird to me.
Yes.
I mean, but supposedly we're learning the stuff for a purpose, and to think that you're not going to lock. Well, I remember one of my daughters is a medical doctor, and she told me how you have to study for the exams, and once the exam is over, you can forget it all. You
I
can't
hear
understand.
this at university too from my friends, and I feel sad because I actually love learning things, and I'm like, I just feel like as a I don't know. I don't think it's my friend's fault. It's just, I think the pressure of perhaps passing the exam maybe kill people's intellectual curiosity. They lose intrinsic motivation. I don't know what it is.
Well, it's a challenge of, I say, the difference between being a student and being a researcher, or you might just say student versus being a practitioner, or being a student or actually mastering the material. In math, the problems you get are going to be, at least in the view of the professor, they're going to be very close to the problems you've studied in homeworks. And you don't get much variation. But if you want to apply it to different kinds of problems, you have to understand it more deeply. Why did this work? What is the relationship? Why is this the tool that I'm using? What is it about it? And I remember in the time I was in beginning high school, so grade 9, we were in a carpool and somebody gave me an algebra problem. And by then we were not studying algebra in middle school. And I could figure out the solution to this puzzle, even though I didn't know how to do algebra. And to me, this was a really neat thing. It really struck me. I think that may have had a real impact on me, that you can actually solve some of these problems without knowing the algebra. Well, it's got to be a pretty simple problem. Nonetheless, looking at problems and trying to understand them, what ideas naturally come up. And the other aspect I put on this is communication. I say it's all about communication of ideas that you've come up with, or ideas that you've put together. It's all about communication from my perspective.
How do you become an effective communicator to others?
Well, there are well, I've been giving these lectures on AI a number of times, and every time I give it, I learn something new about what they don't understand, what I learned something about what I should be saying, what I should be emphasizing, and all of them will contain this idea that 2/3 of the people in the top 20 fast chess are in this 2/3 of the top 20 in slow chess. And why is that? And why is it essential to be able to play fast chess in order to play slow chess? And so the same ideas keep coming up, but it's good to be able to practice these ideas. And I think every teacher will tell you that one of the ways to become a better teacher is to have the students ask questions as you go along, but you can't get the students to ask questions.
How do you get students to ask questions? Obviously it's not the same, but I was teaching Brazilian Jiu-Jitsu last year at the University Society, and I really wanted to get people to ask me things because I only started getting much better at fighting once I just started asking questions on everything. And I found this, my friend sent me all these DVD instructionals for Brazilian Jiu-Jitsu, and I just spent hours finding the bits I wasn't understanding. And because I knew how helpful it was for me, I just sat in the middle of the mats, and there was 30, 40 people. This happened every time for the first 5 sessions, and I just didn't talk. I asked them, does anyone have any questions? And then they said no one answered, and I asked again, and then I just didn't talk until one of them, in a shy manner, asked a question. And that's one method I found of kind of encouraging a student asking something.
Yes,
And then it creates a snowball effect, like you said.
Right.
Any other tools that you use to encourage your students?
Well, you can ask the students questions. I'm trying to understand what you don't understand. Do you understand this? And then maybe somebody else will say they don't understand it. But basically, when you ask for questions, as you said, you have to stop and give them a long, uncomfortable period of time to think up a question.
Almost like it's more uncomfortable to not ask a question than to ask a question now. So they might as well ask it kind of because of.
Okay. And what you're going to do is when you start off, you say to people that interrupt me. You can ask questions as we go along. If you don't understand what I'm saying, ask questions. That's a bit more specific. If you don't understand what I'm saying, just stop me and we'll go into it. And in Zoom lectures, you can't. That doesn't happen. So this talk I gave in India last Sunday was like that. But in any case, I had a good time trying to communicate these ideas.
Is there anything we didn't talk about that you wanted to talk about?
Seems like we've covered a lot of material.
Mm-hmm.
And my emphasis again would be everybody is in charge of their own education. You don't learn unless you're in a very special circumstance by sitting in a class. And now that we have all these opportunities on the web, you can learn a whole lot of different things. But it isn't quick and it isn't easy. If sitting in class, it's not easy. And you can compare notes with other people and see what they listen to, what they read on the same topics. But you are in charge of your own education. And another point I make is that the AI is coming towards us. And if you're not on top of the AI now, get on top of it. If you don't get on top of it, or your children don't get on top of it, then when it hits, they're going to be behind everybody else. It's hitting now. What can I tell you? I don't know how fast it's going to come, but it's coming faster than any technology in the past. So that's my story for today.
How was our conversation? How was the podcast? Did you enjoy it?
Yeah. I enjoy talking to you. I enjoy talking to people. And
I enjoyed it too. It was very informative, and I always have the chance to learn more and more when I start editing the podcast because I listened to it again and again and again, and that's almost as exciting. I learn new things every time I listen to it, although it's the same conversation. I could go on talking to you for ages. I'm aware that you might not be feeling the same, so I just wanted to check in on your endurance level.
well,
I'm
my
happy
feeling
to.
is we've done 2 hours. We might do something else again at a different time. It might be better for your clientele. Yeah.
Cool. Well, I'll leave you in with one last question. I know you don't like life goal type questions, but if you wanted the people that listened to you today to go away with one key takeaway, you just told me obviously about get on top of AI, and yeah, what would that takeaway be? Would it be that or something different?
I think the biggest thing I worry about is people not knowing about AI and not trying it out and not trying it out in enough circumstances. And I can go on and on about not doing enough with AI. And I write computer programs, but I've spent, there was a 20-year period where I've spent 3 or 4 hours a day writing computer programs, but I haven't done that in 20 years. And Now I ask the AI to write the program for me, and it's much faster. And I have to keep correcting it because it doesn't do things correctly. I can't trust it. I got to make sure it's doing the right thing. But computer programs are very good at writing computer programs and all kinds of things. And so if you're in a life of asking questions, then you're naturally going to be asking the AIs and see how many different things you can get out of an AI. Oh, you want to scramble eggs. Well, what's the best way to scramble eggs? At least you'll get some new solutions. If you're scrambling eggs all the time, well, you don't need this, but it's something you can do by asking it such questions, anything, but not predictions about what's going to happen because it's an encyclopedia
Mm-hmm.
that you can talk to.
And you said before also, you almost want to come up with, well, answers to questions that AI would have trouble answering. And and
Well,
that
right.
seems like a difficult task in itself, finding
I
those.
think the main thing is to start asking lots of questions because you've been deprived of being able to ask questions. Either you're sociological because you're in a class and nobody else is asking questions, or the teachers don't like questions, or they don't make time for questions, or any case, you've got such an opportunity now to ask questions of the AI that, or other people, just ask questions. That's what Einstein did. Pretty much all of his biggest discoveries were from saying, well, what happens if he's asking a question and a question that people didn't ask, but it's an understandable question. And the analysis that follows that is also important. But if you don't start with the question, and sometimes he would get collaborators to help him out with parts, and it doesn't mean you have to do the whole job, but asking the right questions. Somebody gives you an equation. Well, where did this equation come from? Is this really the right equation? I mean, that's the way to start. Is this really right for the problem? Maybe it's wrong. The person isn't a mathematician. Let's look into the question of what the right equation might be. Maybe it is the right equation. Constantly asking questions.
Awesome. Talking of questions, so I sit down for podcasts and I prepare a bunch of questions. Some of them being more specific on the person's work, other ones being more big picture questions, other ones being a little bit more creative. So I had hundreds of questions for this podcast, and I don't force the questions if they don't come up in the conversation a lot of the time. I just like having the option of choosing a few here and there when they fit. But yeah, there's so many questions I didn't get to ask you, but I'd be very happy to do this another time too, in the future. There is one that I'm just curious about. I don't want to miss the opportunity. Have you ever come across a really unique and weird uh, uh, exhibition of chaos that you didn't expect? Or
Nothing comes to mind. See, I kind of expect chaos to be everywhere. I mean, and you see, I don't know what questions you're going to ask or what your remarks are going to be. And so I don't know what my remarks are going to be. This is a chaotic situation. And if we were to run this thing again and we started slightly differently, it would evolve in a different way and it would cover some of the same material and not other parts. And so I expect chaos to be pretty much everywhere. Now, when you're dealing with a chaotic world, you make plans. It's like they say with war that you have to make plans, but your plans get destroyed after the first battle or first encounter with the enemy. But you make plans short term. You don't make plans long term, because the long term you envisage isn't going to happen. You apply to various schools and you get into one of them. That completely changes your life. And so I have a saying written on the wall in the math building, and it goes something like that. The most successful people are those who are good at plan B. The most successful people are those who are good at plan B, meaning that your plans aren't going to happen the way you expect, and you have to be able to change plans readily and successfully. And it doesn't say you have to have a plan B in mind, but you have to have, in fact, with the chess playing machine, they have a tree. You have a tree of possibilities, and you want to follow which branch of the tree of moves am I going to follow? And with Alpha Zero, the chess player, it says we want the branch with the most opportunities, the most good branches. Well, that's what they say, and this is what I'm saying. When you don't want to go into a case where you're walking along the edge of a cliff, and if you start to slip, there are no plan Bs. So you want to be doing things where there are lots of options, and then you're good at option B. A lot of different ideas built into that statement. The most successful people are those who are good at plan B, or plan C, or plan D, and so on.
That makes a lot of sense.
That's a chaos theory.
Your favorite, I'm supposed to do a closing of the episode, but questions pop in my mind. But I feel bad because I know you from you have a lot of people you admire in science, and you've mentioned Einstein, you've mentioned Maxwell. I wondered what's the thing you admire the most about your role models.
About my role models?
Yeah.
Well, one of the things, you see, is that you really don't know much about your teachers. And teachers can be your mentors, they say. But what I find is it's easier to have a mentor who is a person you've read a lot about. Okay? And you've never met. Like, I never met Einstein. But you could understand what he's going through. And if I was a student at Maryland, at the University of Maryland, and there's a University of Maryland professor, and he's teaching class, I don't know much about him. So I don't know what is going on in his head. If I read the books about Einstein, I have some idea what's going on in his head. And so your mentors can be people you read about. And for example, your best math students in high school probably think that math is about answering questions. But you read about Einstein, and that's not what it's about. It's about asking questions. And these students simply don't see mathematics. Mathematics is asking questions and answering them, not just answering questions. And not just looking at a system of equations and solving the equations. That's what you're doing in 12 years of math. But the other aspect is learning about people and reading about people and what they do. There was a book, Men of Mathematics. by E.T. Bell. And it was written in the 1930s, but it talks about many mathematicians over the past hundreds of years and what they were thinking about. And this is completely different from what you get if you're sitting in a math class and you're being told how to solve a quadratic equation. Okay? And so you understand the goal of the best people. So reading about the lives of physicists, mathematicians, scientists, it's fascinating. So
Thank you so much for our conversation today. I really, really appreciate it. And I'm very grateful to be learning from you. I wish you all the best, and I hope we speak again soon. If I'm ever in the US, in Maryland, I'll send you an email. And yes, if you have any closing remarks, feel free to tell them.
I think I've gotten my best ideas across. So.
Nice. Well, I'm glad. I hope you have some nice day. Oh, it's 1 p.m. Oh. So you no time for dinner, time for lunch for you. Alrighty.
Okay.
Well, thank you for watching us, guys.
Thanks
And
for inviting me again. So
no, thanks for coming.
again,
It's
thanks for
my
inviting me.
pleasure.
That's what I mean. Right.
Guys, thank you for watching us, and we'll see you in the next episodes. Bye bye.